Well, hello everyone. Welcome back to our OpenFoam discussion on the CHT multi-region foam. And today we want to talk about, first getting our snappyHexMesh working so that we can start adding layers to increase the quality of our mesh. So, yeah, in previous videos, we were talking about some of the experiments I've done that concluded that changing FV schemes would not help, because if you see changing FV schemes here, going to the system, oil, FV schemes. Yeah, I've changed everything. To crank Nicholson to try and stabilize the time schemes. Cell M multi-directional. Cell MD means multi-directional limited. Gauss linear scheme. That is supposed to stabilize the gradient schemes. Change everything here to upwind as far as I can. And even this, which has nothing to do with flux, I've tried to change it to upwind in an attempt to stabilize it. Laplacian schemes also changed to limited corrected. Okay, so meaning to say that the correction factor when it comes, it's kind of like not really corrected anymore, so to speak. Okay, so normally we have the linear things that may cause instability in some cases, for example the bed mesh. Now so we try and limit the effect of those. So no matter how we limit these effects, it's not giving us any good result. Same goes for the interpolation scheme, though the only thing for interpolation is linear there. There's not much option you can change. Alright, so this is what we are left with. Okay, and what's more, we have tried lowering the temperature, lowering the things in the control dict, so system, control dictionary. So we try to change the Coron number below. You can even change the max diffusion number and put it below 1, because this diffusion number is really like, below that's the conduction conduction parameter. So it's how much heat or how quickly the heat flows with respect to time. You can reduce that to lower than 1 and still the instability will grow, and you have those funny oscillations happening. So I mean, of course we can like do a few rounds of more of testing to see where this error is propagating, but that probably you're not going to do that now unless it's really like necessary. We can guess that the problem is the mesh, because it's there are no layers added and it's pretty small. Yeah, it's really small and oddly shaped, so that the mesh quality may be a little bit poor. Okay, so that's the reason why we want to try refining the mesh using something called the snappyHexMesh and the layer addition. So where you will see the non-orthogonal experimental case, this actually changes the FV solutions. Okay, this was another experiment I did, FV solutions, where I changed the non-orthogonal corrector over here to 100, meaning to say that, okay, maybe the orthogonality of the mesh, non-orthogonality of the mesh needed some correction, but of course changing it up or down doesn't really make a difference. The thing still blows up and it's really not working. So yeah, that's how I arrived at the conclusion that, okay, probably we want to have a better mesh first. So we want to have a better mesh. So now we look at the snappy layer at experimental case. So there are a few things probably want to change. First thing first, I would like to copy the FV schemes from my coarse mesh sphere oil, system oil FV schemes into snappy layer addition system oil F. Put there. So I'm gonna put it there. Via the FV schemes. Okay, so this replaces all the changes we made. I made before in the previous videos. I discussed about making changes in the previous video where I changed most of this to a Gauss upwind scheme. So now I want to test the ability of OpenFoam to change the ability of OpenFoam to the effect of changing the mesh on this solution. Okay. Now for these solvers, I'm not going to change much because it's easy to kind of predict. It's easy to predict the effect of all of these, changing any of these values, the residue controls. I think understand them pretty well, not too much of an issue. So, and we can even do a change dictionary. We can see the change dictionary in dictionary. All right. All right. So this is the initial condition, and I want to change it back to 500 just to see if that works. So yeah. Alright, so 500 was the original, so I'm not going to change that. That's what we originally wanted. So the reason why I changed it down to 400 was to see, okay, maybe turbulence. I was suspecting that turbulence was causing the instability, and getting rid of the turbulence didn't change the instability that we saw. So meaning to say the CHT multi-region foam solver kept blowing up with very funny non-physical temperatures. So yeah, that's something I wanted to take a look at. Yep. So this is the thing I want to see. All right, so that you have this 500 Kelvin temperature. Okay, so now what is next? I want to take a look at the snappyHexMesh dictionary. Of course, I'll change the experimental label here. This is for my own note taking. Okay, so in the troubleshooting process, I changed the FV schemes to upwind schemes. It doesn't seem to improve stability. Therefore, I'm going to try some snappyHexMesh options. For example, adding layers. So this is what exactly I'm doing now. So the label for this experiment is correct. These are just my own note-taking procedures. So let's take a look at snappyHexMesh. So we have a pretty clean case now. So I want all three of these to be true. Normally this add layers option is false, at least in the original snappyHexMesh dictionary. Just make sure it is true. Okay, geometry, nothing changes here. Castellated mesh controls, nothing changes. Okay, so the surface-based refinement, I want to change it back to level 2. And just see whether, we are able to get a good boundary. We are able to resolve the mesh of the boundary layer without using too much of these refinements. Because if we don't have to make the the refinements. I mean, we don't have to make the mesh so fine, then don't do it, because one, it might cause instability. Two, I think it's more important, it eats up a lot of computational space, power. Yeah. So where we want to do is not step controls, it is in the add layer controls. Okay. So normally the OpenFoam guide over here will talk about this layer addition and snappyHexMesh. I'll just put these links into the description. Okay, video description. Yeah, so yeah, how does this thing work? Firstly, you have this thing called relative sizes. Relative sizes means that, okay, okay, I'm going to delete all of this. So let's say you have some arbitrary surface, right? And then you want to start adding layers, and you have a very, a very blocky mesh that was generated by the castellated mesh controls. So you have something like that. And what add layers will do is to replace all of this with something that's conforming to the surface. Okay, hopefully you have layers that conform to the surface. And of course, the natural way is for layers near the surface to be very fine, right? Because you want to resolve those. You have layers in the surface, near the surface, to be very fine. But as you go out of the surface, the mesh size increases. Okay, mesh size increases as you go away from the surface. Okay, away from surface. So away from the surface, the mesh size increases. That's what you want. So how do you control it? It is by this expansion ratio, and you turn on the relative sizes control. So where you have that is in this layer addition. Okay. Okay, relative sizes. So when switched to no, the layer thickness is set in meters. When switched to yes, okay. So of course when you say no, the layer thickness is set in meters, meaning to say you yourself will determine you yourself will determine the actual size of the layer, which is entirely possible. Okay, so when switched to yes, the size is determined from the undistorted cell size outside the layer. Setting the thickness in absolute scale will result in constant thickness, alright, of the layers, ignoring local refinement along the surface. So yeah, what does this mean? Let's get paint. Alright, so if you had your snappyHexMesh, do some refinement along the surface. Okay, and then remember you drew those little boxes in the refinement. If you select something of relative size, it will take a look at these boxes here, and you'll try to make the mesh size of the layers at least similar in magnitude to these boxes, the size of the mesh. If you choose like an absolute, if you don't choose a relative layer, then you will just arbitrarily define layer size, and you will not care about the refinement. This may or may not be helpful. So it's helpful if you want to like make the mesh less fine, and you kind of just ignore, and you just say, okay, I want this mesh to be this particular size. I want to have a lot of control over it. But if not, then we can use these relative sizes. So, and when we switch on relative sizes, we can use this thing called expansion ratio, and this calculates the relative size to the prescribed thickness of either the first or final layer. So I mean, okay, we can start playing with some of these things. Okay, so technically, learning snappyHexMesh, you should already know this, but okay, we'll just go through some of these settings just to see the effects on the mesh. Alright, especially now that it's so important in the natural convection setting. Okay, so add layer control, relative sizes true. Okay, so we'll just give these things set this at default, except for this part where it says layers. Okay, so how does this add layer control work? The thing is that for each patch, right? Let's say you have the box and the sphere I was talking about. Okay, each of these will be its own patch. If you don't specify how you want to add layers, OpenFoam or snappyHexMesh will say, okay, I'm going to add layers to every single patch, even though that's not what we really want. The only patch we want to really add these layers on are around the sphere, because that's where it is critical to add the patch. Add the layers. So this is the one we want. Okay. We want layers here. Okay. We want layers here. So, and we don't want them anywhere else. Okay, so if we want this, we want the layers to be 0. Yeah, so we look at in the layer addition, under layer addition, we have this global parameters and layer specification. So patches grow on the layers. Patches to grow on layers, and they can be specified in various ways. Each patch can have a different setup, and where unspecified, the global parameters apply. So what are the global parameters? All of these are the global parameters. Alright, these are the global parameters. All of these that you see here. Blah blah blah. Okay, so if you don't want any what do you call that, growth, okay, to disable mesh shrinking and layer growth on a particular patch, set end surface layers, have it set to 0. Okay, so I don't want it on my max y, min y, max x, min x, etc, etc. So this is what I will do. Min y, and I'll just copy and paste all of this. Min x, max x. I'll save this first. Min z, max z. So this will make sure that, okay, at all the boundaries of the box, I do not want any layer growth. The only one I want layer growth in is the oil to sphere patch, or sphere to oil patch. I'm not really sure which patch will come out, after snappyHexMesh has generated, because, okay, what do I mean by that? Right, and quit. Okay, so what do I mean by that? If you see the all run serial, all run serial pre. So you see in the all run dictionary, or at least the all run serial, what happens first is that block mesh is run, then surface feature extract, then snappyHexMesh and split mesh regions. Of course, you have this restore 0 directory. So the thing is, with split mesh regions, you have two regions, right? One is called the sphere, and the other one's called oil. With this, then the patch on the surface, okay, when you split it up, it will become sphere to oil, and this patch over here from the oil to the sphere, we will call it oil to sphere, right? So that's why, yeah, that's what happens during the split mesh regions. However, snappyHexMesh runs before split mesh region ever even starts. So there is one additional patch, so to speak, where you have to do this layer addition thing. Okay, so how are we going to get this done? How are we going to add the layers properly so that we can, carry on our business? So one possibility is, of course, to run snappyHexMesh after the split mesh regions, so that you can do what you need to do. Okay, and the other option is to run snappyHexMesh so that the layers are added according to the surface. Okay, so that on the spherical surface before you do the split mesh regions. So we can try going to system, okay, and you go to snappyHexMesh dictionary. Okay, so the layers, maybe the thing is, okay, we can try using the STL file first. Can try using the sphere file first to do this layer addition. So let's try sphere, and then we'll put 3 layers here, and then we'll just put the semicolon, save and quit. See whether this is the correct way of running the thing. So we can take a look at all run serial pre, and yeah, that's what we kind of want to run. So let's do all run serial pre and see what happens. So I'm going to change directory to the main directory, and go to change diction. No, I go to GitHub, OpenFoam Heat Transfer, and CHD. Let's go to Snappy. Okay, Snappy layer addition. Experimental case, and we take a look at the log of snappyHexMesh dictionary. snappyHexMesh, yeah. Okay, it looks like it's adding pretty nicely. So, alright, so this is the morphing iterations, which should be part of the castellated mesh castellation, which means there is some sort of snapping it's being done. So they do all the merging and everything is done there. Now, of course, we want to see whether this thing actually pumps out or gives the results we want. So we can do a touch sphere.foam. Okay, so I'm gonna close this and Paraview. This I'm opening Paraview, going to the case of Snappy Layer Add, and to see the thing, of course, we can use wireframe to visualize the what's going on. Okay, so this is the sphere, and we can add a slice filter. The slice filter should be use a wireframe. Okay, so this is a level 2 refinement, which is pretty okay, except of course the mesh is still pretty coarse. Okay, so whoopsie. Oh yeah. Just move the slice there. Of course, we already see there's something a little off with this case. The layer addition isn't really behaving the way we want. So there is some what do you call that? Yeah, some things we need to settle. Okay, so right. So yeah, obviously our adding layer is not working, and there are workarounds for this layer addition problem, because you don't really have a patch, so to speak, at the points where you start refining this surface yet. So yeah, you by and large you should have layer addition, specified for each of the patches. But before you do a split mesh region, there is no patch here, so to speak. There is a surface, and there are now like 2 cell regions, but there's no patch yet. If there is no patch, then there could be some difficulty when it comes to adding layers, because OpenFoam will want to say, okay, where is this patch talking about? Okay, so alright, the discussion on how this will be done continue in the next video. Thanks for watching. I'll see you guys again. Bye bye.